Formation of an enolate ion. We know that if you want to synthesize the enolate ion, we have to start from a carbonyl compound. But what kind of base do we have to use in order to abstract the alpha hydrogen from the carbonyl compound? Okay, let's say that we are going to use the hydroxide ion as the base. Okay, so in which case the hydroxide ion is going to go grab these alpha hydrogens. So there are two alpha hydrogens. One of these alpha hydrogens will be abstracted, and it will give us the enolate ion. Let's complete this equation. So here, this hydroxide ion will go and abstract this hydrogen, thrust these electrons onto carbon. That's going to give us an enolate ion. Which will be resonance stabilized. So here is the enolate ion, and it will be resonance stabilized. So this is the other resonance contributor. And of course, this is going to be our conjugate base. And during this process, obviously, you will also be getting the conjugate acid. Here in this case, water will be the conjugate acid. Right? Because as this hydroxide ion goes and abstracts this hydrogen, water will be formed. Now let's compare the pK values of the two acids in this reaction. So on the left, we have the carbonyl compound standing at pK value of 17. And on the right, we have water as the conjugate acid, which has a pK value of about 50. Now we know that when you have an equilibrium reaction, the reaction will always favor the weak acid. Now between these two, which one is a weak acid? Obviously, this carbonyl compound, which has a higher pK, will be the weak acid, and therefore the reaction is actually going to go favor the reactants. Okay, so the reaction will be favoring the reactants. So which means that if you're going to use hydroxide ion as the base, then you will not be forming enough enolate. When we use a more stronger base than hydroxide ion, then we can definitely form the enolate ion. And one such strong base is LDA. LDA is lithium diisopropylamide, and it has this structure. Now let's use LDA as the base and complete this reaction. The LDA will go and abstract one of these alpha hydrogens right here and thrust these electrons to form the enolate ion, which will be resonance stabilized with the other resonance contributor. Here are the resonance contributors of the enolate ion, and along with that, it is also going to form as lithium diisopropylamine. That would be the conjugate acid in this reaction. This has a pKa value of 35. Now between these two acids right here, so we have the carbonyl compound which has a pKa value of 17, and we also have the diisopropylamine which has a pKa value of 35. Between these two, obviously we can say that this is the weak acid, and the reaction is going to favor the formation of the weak acid, right? So it's going to go in this direction. So if you want to synthesize the enolate ion, then we have to use lithium diisopropylamide and not hydroxide ion. When you use either hydroxide ion or the alkoxide ion, not enough of the enolate ion will be produced. Say for example, for this particular reaction, there is only 0.1% of the enolate ion will be formed. We know that the nitrogen bases are strong bases, and therefore they can go and abstract this alpha hydrogen, but nitrogen bases have the ability to act as a nucleophile where it can go and attack this electrophilic carbon and thrust these electrons onto oxygen without abstracting this alpha hydrogen. And therefore we cannot use nitrogen base, although they are very strong bases. Also, we might be thinking that this LDA, where it has lone pairs of electrons present on nitrogen, can go and attack this electrophilic carbon and do a nucleophilic reaction. But these bulky groups right here, these isopropyl groups, are going to prevent it from acting as a nucleophile. Because of this, we can definitely say that LDA is a strong base, but it's a poor nucleophile. How to synthesize LDA? LDA can be easily prepared by reacting diisopropylamine with butyllithium. This is diisopropylamine and this is butyllithium. And butyllithium is an organometallic compound in which the R group right here is going to have a partial negative charge because you do have an adjacent metal atom. This carbon right here will go and grab this hydrogen and will push in those electrons onto nitrogen. So nitrogen can have extra lone pair of electrons. So let's write down the structures that we'll be getting. So your nitrogen is going to have extra lone pairs of electron, and therefore it's going to have a negative charge. And because it is negatively charged, now the metal is going to get coordinated with it, forming the lithium diisopropylamide. and then along with that we will also form butane, right? Because this is going and grabbing the hydrogen, and therefore this part right here should be butane. Let's compare the pK values of the two acids in this reaction. So here this is an acid and this would be the conjugate acid, right? So this is the base. This would be the conjugate base. Now when you compare the pK values of these two acids, the pK value of diisopropylamine is 35 and the pK value of alkane is generally about 60, right? Or even greater than 60. So we can definitely say that this is the weak acid and the reaction is definitely going to go on the right side. So by reacting diisopropylamine with butyllithium, yes, it's possible for us to form LDA.